Hi, this is Greg Smith from the Department of Applied Science and the Neuroscience program at the College of William and Mary. I wanted to do an example of phase plane and linear stability analysis using a new document camera that I purchased, and I think that you might like this better than the previous versions of the movies that I've been creating. Um, so let's get started. The ODE system that we're looking at is dx dt equals minus 2x plus 2x squared, and dy dt is equal to minus 3x plus y plus 3x squared. So this is a nonlinear system of differential equations. It's a 2D system, so we can use phase plane analysis. And to start, let me just indicate that this right-hand side of the first differential equation we'll call the function f, and the right-hand side of the second differential equation we'll call the function g. Now, to begin the phase plane analysis, why don't we first see if we can easily determine the nullclines of this system. So the x nullcline will be determined by setting the left-hand side of the first differential equation to 0. So that's 0 equals minus 2x plus 2x squared. This can be factored. We can pull out a 2x, so this is equal to 2x times negative 1 plus x, which is 2x times x minus 1. So the x nullcline are all the points satisfying 0 equals 2x times quantity x minus 1, which is the same as 0 equals x times x minus 1, just dividing both sides by 2. So the x nullcline is given by x being equal to 0 or x being equal to 1. So the x nullcline will have two branches, and they'll both be vertical lines. So let me see if I can sketch that for you. This is the y-axis and the x-axis. And if this is the point 1, then the x nullcline, if I sketch it in blue, will be this vertical line going through x equals 1, as well as a vertical line going through x equals 0. So note that the x nullcline in blue here doesn't, it's not continuous, it's not contiguous. There's actually two lines that where the rate of change of x is going to be equal to 0 on any of the points on either of those two lines. Now for the y nullcline, the condition is setting the y nullcline, the rate of change of y equal to 0. And so that's 0 equals minus 3x plus y plus 3x squared. And it looks like if we bring everything but y over to the left, we'll have 3x minus 3x squared is equal to y. And then we can let's sort of flip this around and say y equals, and then we'll factor out the 3x. We'll get 3x times 1 minus x. So this is the equation for the y nullcline, and it will be a concave down parabola. I can see that because of the negative sign in front of the x squared term. And this concave down parabola will intersect the horizontal axis at 0 and 1. So I'll attempt to sketch a concave down parabola that intersects the horizontal axis at 0 and 1. Alright, so this is the equation for the y nullcline. Any set of points x and y that satisfy that equation will be on the red line, and this is the equation or equations for the x nullcline here. So we know now that certainly that there's two steady states. There's 2 points in the plane where the x and the y nullclines actually meet. So when we consider the steady states, that's quite easy to see now. So one steady state is both x and y being equal to 0. And that's this one. And there's another steady state, which is x and y being equal to 1 for x and 0 for y. And that's to the right. So what else can we do? Well, in addition to determining that these steady states are occur at the particular values of x and y that we've indicated, we can also analyze the stability of those two steady states. I think in this case I'll do that even before I sketch any flow on the phase plane. So remember, in order to do that, we're going to calculate something called the Jacobian. So this is now linear stability analysis of those two steady states. What is the Jacobian of this system? It's a function of x and y potentially, and it's the partial derivative of the first equation with respect to the first variable, and then the partial derivative of the first equation with respect to the second variable. This element is the partial derivative of the second equation with respect to the first variable, and this element is the partial derivative of the second equation with respect to the second variable. And if we calculate those partial derivatives, we'll get the Jacobian matrix. So up here we see that f of xy is minus 2x plus 2x squared. So the derivative of that function with respect to x is minus 2 plus 4x. The derivative of that function with respect to y is 0. Now g of x is minus 3x plus y plus 3x squared. The derivative of that function with respect to x is minus 3. The derivative of the partial derivative of g, the function g of xy with respect to x, when we take the derivative of the y here, we're thinking of y as a constant, and so we'll get 0. And then the 3x squared term will yield 6x. The partial derivative of g with respect to y is just positive 1. And now to do linear stability analysis, we need to evaluate this Jacobian at the two steady states. So the Jacobian at the first steady state, 0, 0, is the constant coefficient matrix minus 2, 0, and minus 3, 1. And the Jacobian matrix at the steady state, 1, 0, is equal to minus 2 plus 4 times 1, so that's plus 2. Here we have, if x is 1, we'll have plus 3, and then we'll still have 0 and 1 over here. So those are our two Jacobian matrices. And to continue the linear stability analysis, let's consider the trace and the determinant of these two matrices. So the trace of this Jacobian matrix is negative 1, and the determinant in this case is minus 2 times 1 minus 0 times negative 3, so that's simply minus 2. In this case, the trace is 2 plus 1, or 3, and the determinant is 2 times 1 minus 0 times 3, or positive 2. So we can see here that neither of these equilibria will be stable, because the condition for stability is that the trace is negative and the determinant is positive, and neither of these two satisfy that. So both are unstable. So now let's see if we can sketch some, get a little bit more information about the solutions in the phase plane. A solution crossing an x nullcline can only do so in the vertical direction, because the rate of change of x has to be 0. So it's pretty clear that both of these vertical nullclines for x are separatrixes. The solutions are not going to be able to move from one side of those lines to another, right? Because if you were on one of the x nullcline, the rate of change of x is 0, so you can't move to the left or to the right. You can only move up or down. So in fact, you can actually see that these lines will, there'll be trajectories or solutions that are actually following these nullclines. We'll see that in a minute. With the, for the y nullcline, the rate of change of y is 0, and that if the y nullcline is going to be crossed, we're going to have to do so in a horizontal way. Right? Because moving horizontally is the rate of change of y being 0, but x being non-zero. Now, can we figure out the actual direction that things would be moving in the various quadrants? That's not too difficult. So the right-hand side of this differential equation, minus 2x plus 2x squared, right, is equal to 2x times x minus 1. So if x is very large, it's greater than negative 1. It's greater, and it's greater than 1, so we're over here, right? Both of these terms, 2x and x minus 1, will be positive, and the rate of change of x will be positive. Now, when x is between 1 and 0, the rate of change of x will be negative, and when x is is less than 0, the rate of change of x will be positive again. The y nullcline also separates the phase space into two domains where the rate of change of y is increasing in one and decreasing in the other. When let's see, if we look up here, we can write the right-hand side as y. minus 3x times 1 minus x. And this means that if y is greater than 3x times 1 minus x, meaning we're above the parabola, the rate of change of y will be positive. And if y is less than 3x times 1 minus x, the rate of change of y will be negative. So up here above the parabola, the rate of change of y is positive, and below the parabola, the rate of change of y is negative. So we could indicate the direction of movement in all of these different regions in the following way. One thing we can do is actually put arrows on the lines crossing the y nullcline. In this region, the rate of change of x is positive, so the arrows should be pointing to the right. In this region, the rate of change of x is negative, so the arrow goes to the left, and it's positive again here. And now these arrows won't represent solutions, but in this region where x, the rate of change of x is positive and the rate of change of y is positive, right, that would be indicated by an arrow going to the northeast. Here the rate of change of x has shifted, but y is still increasing, so it goes to the northwest, and here it should point to the northeast again. What about down here? So when we move from this domain to this, the sign of the rate of change of y changes, so this will now be pointing to the southeast. Southwest and southeast. This region is the same as this one, so it's also moving in that direction. This region is the same as that, meaning there's no nullcline that separated those two regions of the plane. So that's pretty good. We know that that both of these equilibrium are unstable. Both the equilibria are unstable. We've got a lot of information about the direction of the flow in the phase plane. And we can see, just sort of think about what's going on near the steady states and see if we can get a little more of a sense of what's happening. So, for example, if I was on this point here on the x nullcline, the rate of change of x is 0, but we're also in a region where the rate of change of y is positive, so there is a solution that goes vertically in this direction, here and here, and there's a solutions that go down in this direction. Now how do I know that? Anywhere on this nullcline, the rate of change of x is 0, and I've already determined the rate of change of y. So I'm on the nullcline, I'm going to stay on the nullcline, and I know whether I move up or down. So if you just sort of look closely at this equilibrium point, in this region near the direction of flow is away in that direction to the northwest, and in this region the direction of flow is to the sorry, this is northeast. The direction of flow here is southeast. The direction of flow here is southwest, and the direction of flow here is northwest. So that sure does look like it's going to be a node. We already know it was unstable, so it's an unstable node. And this one, if I do the same thing and think about what's happening nearby the flow is moving to the northeast over here. It's moving to the southwest in this region. And this region is moving in that direction, southeast. And in this region up here is moving northwest. So when I look at these flows, this looks very much to me like a saddle, because if a solution was moving in this direction and then crossing the nullcline in that direction, and then it would have to move down, and it would asymptotically approach that axis. If a solution actually crossed this nullcline in this direction, it would then move upwards like that. So you see how it looks like there's just some indication here that this is going to be a saddle. Saddles are unstable, which is consistent with what we have here. So I'm thinking that this is going to be an unstable node, and that this will be, 0, 0 was the saddle. So this is a saddle, and this is a node. And I can confirm this algebraically by considering the eigenvalues of the Jacobian matrix evaluated at these two equilibria. So to figure out what those eigenvalues are, remember that an eigenvalue is going to be the opposite of the trace of the Jacobian, plus or minus the square root of the square of the trace minus 4 times the determinant divided by 2. We haven't discussed this in class yet, but this is the solutions of what are called the characteristic equation of the 2 by 2 matrix when we're solving an eigenvector-eigenvalue problem. If you just take it as a given that this is a formula for the eigenvalues of these constant coefficient 2 by 2 matrices that we see here, and do a little substitutions, several substitutions, you'll find that I did this in advance actually. So one of the eigenvalues in this case is -2, and another one is 1. So these are real numbers, and one's positive and the other is negative. That corresponds to a saddle. In this case, one of the eigenvalues is 2, positive 2, and the other eigenvalue is positive 1. So these are real and distinct eigenvalues that are both positive, and that corresponds to the unstable node. And you can check my work here. You can let me just do one of these. One of the eigenvalues was -2 here, and one is 1. So if I, the beta is the trace of the Jacobian, so if I take -1 for beta, and if gamma is actually -2, then this will be -1 squared, which is 1, minus 4 times -2. 1 minus 4 times -2. So that is 4 minus 4 times -2 is 8. And I add 1 and I get 9. And then I take the square root of that and I get 3. And then beta here again was -1. So it's -1 plus or minus 3 divided by 2. And in one case, that gives me -1 plus 3, or 2, divided by 2, which gives 1. And then the other case is -1 minus 3, which is minus 4 divided by 2, which gives me -2. So you can put these values for the trace into the determinant into this equation here to get these two values for the eigenvalues. So I hope that helped. I kind of just worked through this on the fly, not thinking about it much in advance, and we seem to have been able to figure out quite a bit about the direction of flow in the phase plane, how many equilibria there are, and even to some extent classifying equilibria. Just by considering the trace and the determinant, we knew that they were unstable, and a little more work with the eigenvalues shows that one is a saddle and the other is an unstable node. And that was actually what I guessed was going on based on the direction of the flow near the equilibria as well. Good luck with your next problem set, and I'll see you in class.